I'm Ronnie. Some of you I know and some of you know me. I thought there are more students, but okay. If not, then it's more family-like. Just let me get an overview who is here. Gil, Zeev, Yehuda.
He's on Zoom.
Yehuda on Zoom.
Yeah.
Is he already? Maybe I should share the records. He didn't. He cannot be there because I didn't share a link.
Maybe there's a class link, but he sent us the picture of us sitting here, so I think he loves that.
There's the camera.
Okay. אורן, אפשר להדליק את זה?
אז הדלקתם?
זה שם? אוקיי. So maybe there's also recording on Google Meet or something.
Yeah, I think so.
Automatically. Okay. Good, then I don't need to share a link, then anyway I can see it. Also, you cannot ask questions then, so it would be better.
He's on YouTube, it says.
Yes, should I?
Maybe you can ask questions by the chat on YouTube, but I don't think we have access for that.
No, let me put the link on Moodle. Okay, then. Good, this should work, I hope. So if it goes directly to YouTube, I don't need to record it, right? It's on YouTube. Good. Okay. So, Yehuda, you said it's he's online. Okay. Then we have Metal. Ronit. Did they print the right course here? Nitzan. Yeah. Okay. Nitzan is here. Then Emil we have, of course. Then we have. Joe King, Chinese fellow, also not, and Or, yes, I know you from Mother, right? You were Mother?
No, I think a few years ago we had a course.
Yes. What course was it?
Something like complex systems. You have a course for the third
computational physics?
Exactly,
okay,
this one.
Computational physics, okay. Good.
Just saying that
yes.
Metal is on Zoom.
Metal is also on Zoom?
Yes.
Okay. So Metal is on Zoom. And Yarden. No. So then Joseph,
Shy.
Shy. Ah, yeah, you are from
Yeah.
Ilanit, right?
Right.
Good. Okay. Okay. Shy, maybe you also register that you get, or you send me your ID and I register you, that you get the emails that I send on Moodle. Otherwise, you yeah, good. So, welcome to Complex Systems, and this year I want to try something new. I mean, I take part of the course that I was teaching 2 years ago, but there are two things that happened meanwhile. One is that my teaching assistant is already now a postdoc in Boston, and he gave all the programming background and stuff, and and since I didn't find a replacement, it will be less heavily on programming. So, you know. And second thing that happened is that the university found a new educational center or something, and they give money to get students to more applied things, you know. And what I suggested is that we will go to visit 4 labs, research labs, 2 in Berlin, 1 in Shiba and 1 in Ichilov, where we record data and analyze data. That you get an overview of why the stuff that you are learning is good, you know. I mean, is not for nothing. And it will be like this, that we will sponsor as a bus, and then we go by bus to Ichilov and by bus to Shiba. Shiba's a little joke because you could just walk there, but it's more efficient to go there by bus. And so this would be basically the syllabus and the schedule. Today we have a general introduction on complex systems. So basically the first 4 lectures will be theory, complex systems, and methods in complex systems. And next week, for example, we will discuss we will ask try to answer the question why there are no giants, and this is related to scaling theory. And the third lecture will be on fractals in math, in nature. Everybody knows what is a fractal in math and in nature, but we also have fractality in time series, that we will learn why we have this and how to analyze it, you know. And this will be important for our lab visits also, because some of the labs, they use exactly this approach to analyze their data. Then there will be one topic or 2 lectures basically on EEG. The first part will be on the background of EEG, learning what EEG is, so how we analyze EEGs, for what it is good for. And then we have the first lab visit in Ivanit's lab, and we will have to find someone, you guys, who is a volunteer that we can measure the EEG for him or her. The next lab visit will be related to human posture, and we will go to the virtual reality lab in Shiba. There's only it's a big virtual reality lab in a dome, right? And they only have, I think, 3 such labs in the world. Another one is in Texas, and the third one I forgot. But one is in Israel also, right? So we should go to visit there. Then there will be a Hanukkah break. After the Hanukkah break, we will discuss the results of these 2 lab visits. We will have some tasks to analyze the data, and then we discuss what you got out from them. Then after this we have another lab visit to Irland, where we learn about human locomotion, walking, and what you can detect by studying just how people are moving. Probably you know that when I go on campus without classes, I mean I see very badly without classes, right? And I cannot even see shy, you know, when I take off my glasses. But when I see somebody from far away, without even recognizing who it is by face, I can already, by the way he or she is walking, I know who it is, you know, if I know this person. And because our gait is like a fingerprint, okay? So it's very characteristic. And even there are a couple of nuclear power plants in the US and in Europe where you do not scan the iris when you want to enter to the lab or your fingerprint, but you walk along the corridor and your gait is monitored by different cameras, and then the computer decides if it's somebody who has access, who can enter or who cannot enter, who has access or not. So this is the topic of point number 8, and point number 9 will be our last topic, the MEG lab in Gondar. There's also only one MEG lab in Israel, and this is the one in Gondar, and we will learn about MEG. Good. How about grades? Here, the most important is hidden. So, since I don't have a teaching assistant, it's difficult for me to, during the semester, to check all the time exercises. So I suggest to do the following, that you prepare a course notebook, okay? So the course notebook, I will tell you a couple of things about it on the next slide, but the course notebook will be the majority of the points you're going to get. So the maximum number of points for an excellent course notebook is 80, and then I have a couple of tasks during the semester that also give points, okay? More about this on the next slide here. So course notebook, it will be a Jupyter notebook. I don't know if someone familiar of you with Jupyter notebook and Colab.
It's very similar to Google Colab.
Yeah, it is actually Google Colab. In Google Colab you work with Jupyter notebook. And so you don't need a grade here, right? You already got all your grades, so you don't. So I cannot even ask from you to do anything.
No, it's okay.
Yeah?
It's
so,
it's an interface. You can work in Python using it.
Yeah, but not everybody is familiar with
so I send you a link.
Google Colab and Jupyter Notebook. I was actually hoping that someone can next week give a short introduction what Colab and Jupyter Notebook is.
Sure.
This would have been 10 points.
No, it's okay.
So
I will make a short slide.
I would be happy if you can, for 10-15 minutes, explain everybody
how to get in,
what to do, and
how to do the basics.
That you can do programming inside. You can write like in LaTeX, and you can include pictures and stuff like this, because this is students have to know, you know, the basics. Good. So this will be the first task. Now we have, if you only are so little, then I have to cut the list of tasks, because now I put a lot of tasks, and good, but let's see. So the second task will be to give a background on EEG. This is more like what is EEG, what are the characteristics of EEG, how to analyze EEG in general. The theory would be 10 points, then to write a script in Jupyter Notebook that everybody can use later for their analysis, that does fast Fourier transform and bandpass filter, because this we are going to use. This would be 15 points. I mean, you can go through the list later and just tell me what tasks you think you can do. We will do it like this, that someone, so for example, if you wrote a script on FFT and bandpass filters, that you briefly introduce it, 10 minutes, 15 minutes to the students, and then upload this to GitHub. We will have some GitHub repository, and then everybody can go to GitHub, get from there the script for their analysis, to include it in their notebook, right? So that's the idea behind. Yeah, any questions on this?
Yeah, I don't really understand. Is it a group project, or is it a standalone for each one of us to do all of this tasks to get the 80 points?
No, this is one of you will decide which task they are going to do, but it's for the benefit of the group. So you will, but only you will write, for example, the script for FFT and bandpass filtering. You will explain your program, test it, and upload it to GitHub for everybody to use.
And then I get 15 points.
And then you get 15 points if everybody's happy with you. We will do some.
And how can I get 80 points for?
The 80 points you get at the end of the semester. At the end of the semester, you compile your notebook. So the notebook is your personal summary of the course. Okay, so you will write there. Complex systems are this and this and this, and we learned about fractals, and we learned about this, and you include your analysis. For example, when we go to record EEG data, you put there your results. When we go to the gate lab, you include your programs and results. And at the end of the semester, you submit it to me, and I'm grading it. And if it's perfect, you get 80. And if not, you get less points, right? But important is that your notebook has some personal touch, okay? I mean, now with ChatGPT around, you can do a lot with ChatGPT, but I will see it, because I also do a lot of ChatGPT, and I can see it. It's, for example, I had now an application. I was doing reviewing for the German academic exchange service, and there were students that applied for scholarship, and their motivation letter was written by ChatGPT. You notice this because it didn't have no personal touch, you know, and also how ChatGPT is writing is, you know, you read a couple of such letters and you know. So don't do this, okay? It's not. It's also not good for you. I want you use ChatGPT to learn stuff, but try to translate it into your own words, okay? This helps you more to really internalize a topic. Good. So that's about tasks and notebook. Any other questions? So I thought at the beginning, I saw there are 10 students. I thought we do tasks, 16 to 20 tasks. Everybody's doing 2 tasks, so he or she has the chance to get 100. Now we are less students perhaps, so I have to reconsider the number of tasks. But let's do it while the semester is progressing. Good. So if there are no questions, here's a list of books that are about complex systems. We will not. I mean, for the course, I took from each book a little bit, you know. So they are very. I mean, the first 2 books are perhaps the closest to the course curriculum, to the beginning of the course curriculum. Other books are very specific. So, for example, Feder has a book about fractals, going very deeply into fractals that we will not go in this depth, right? But if you're interested, there are very nice books I worked with when I was a student, and you can learn a lot of them, but it's also challenging, you know. Yeah, good. And what everything you need to solve the problems we are discussing, you will learn in class. Good. So let's start with complex systems and with the question, can we predict the future? What's your opinion on this? Can we predict the future? Very philosophic and religious question asked over many centuries and discussed by many philosophers and physicists and mathematicians. So what's your opinion? Everybody should have an opinion on this. Can we predict the future? Ingrid, what do you say?
We can predict with a very high precision or high percentage what will happen in a certain specific mechanisms and systems. Okay. We can predict the outcome of few things, but when there are many systems involved together, sometimes when the outcome of one system, it might interfere with another, so then it will get much more difficult.
Yes. Okay. That's pretty good. Shai, what do you think?
It's really.
I mean, I asked this question now. I want to hear what you're saying, and then I will ask the question again at the end of the class. And then I want to see what you would say differently.
I would say that in some topics it's almost impossible to do it right now, nowadays. Specifically in psychological processes and brain activity for a long time.
But if you had unlimited computer power, could you then predict?
Eventually, I think that maybe as more as specific we are, we can predict a good prediction. But as long as we do something wider and wider, I think it's very difficult.
Okay. With what? What's your?
There are so many perturbations in life and in the micro scale.
Okay, so you're good now to life. Okay, also interesting.
Yeah, I mean.
I didn't say your future of life. I say future in general. But you
in space, let's say, not life itself, but even when you deposit energy in a molecule, you don't know exactly how this energy will disperse throughout all modes.
Okay.
So it's very hard to predict because there are so many possibilities, and maybe you can predict different types of futures, and maybe one of them will work. But
like the multiverse, right?
You can call that multiverse, but I call that
the Marvel universe. We have a multiverse, and
something like that, but something that you can just measure the possibilities.
Interesting, yes. Joseph, what do you say?
I also think you can just know the possibility. You can't know which future exactly will happen.
Okay, good. And Nitzan?
Yes. I also think about the possibility that if maybe we would have enough, we know about the starting point. We would know enough about it, we can make a good assumption for where we would go.
Okay.
But still consider all the possibilities.
It's good, it goes in the direction of chaos theory. So you all touched important points that I tried to cover. And just from the question you see, it's a complex question, right? It's something that I thought is maybe good to start at the beginning of a complex systems course. And so let's discuss a little bit along this. But first, let's talk about complex systems. What are complex systems in general? Okay, what is their structure, organization? And the first thing to know is that complex systems have intermediate number of particles or components, so to say, right? More than a few parts, but less than too many. Why this is important, we will see in a minute. We have different length scales, or different scales in general, different length scales, different time scales. It's not just one thing, you know, it's many different sizes that play a role. We have coupling among the parts, among the particles in the complex system, or it's humans, it's among the humans, right? And non-linear, you know what means non-linear, right? Just for the so a linear relationship is like a spring, right? We know this from mechanics, that Hooke's law is a linear law, but if you would have a non-linear interaction, it would not, so the force, you pull something apart or you put something against each other is not proportional just by the distance, right? So this would be a non-linear interaction. We have feedback loops, we have feed-forward interactions. It's not just a simple superposition. So complex systems, basically, to summarize these 3 points, is more than the sum of its parts. Okay, you cannot just by looking at the ingredients and knowing their interactions, you still cannot say how the system will behave. Okay. Another point is that complex systems are usually open systems, not like in thermodynamics, where we usually look at the closed system at equilibrium. Here we have an open system that does not have well-defined borders, and there is no equilibrium in the sense of a thermodynamic equilibrium. The systems have memory, so it is important to the system what happened in the past to what will happen at this moment or in the future. Okay, also an important point. Then we have the subsystems of complex systems are complex themselves, and just to make to state the difference between complicated and complex, usually engineered systems are not so much complex, they are complicated. A car is complicated, right? It has many different parts, it's complicated, but it's not complex. It's not surprising how the car behaves, so to say. But life, I mean, we say life is complicated, but life is more complex than complicated, right? So you can have, let's say, an exception for an engineered system that is complex is actually the laser also. But let's stick with life. You can have, imagine you have identical twins. Okay, identical twins. They have the same genetic code. They grow up in the same household with the same parents. They get the same school education. And imagine they are going to play soccer together. Okay, but now one of them gets injured in one of the games, and as a result will not become a famous soccer player as his brother or her sister. Okay, so it's not deterministic, so to say. It's complex. So nonlinearity, we already talked about it. Nonlinear interactions play an important role. They are usually local, but they affect the system on the global scale. Okay, and an important property of a complex system is emergence. Okay, you get something interesting that's happening with the system. So an emergent property at a certain level that originates from interactions at another level. So you can have, for example, simple initial conditions, and you get a complex structure in dynamics. We will have an example later that starts with very simple conditions, but results in something that is complex. And this would be what is called emerging complexity. Okay, we can also have the opposite. We can have complicated initial conditions, and everything gets simple. So this is then emerging simplicity, just for you to have it heard one time. Then we have the property of self-organization or self-regulation, also important for complex systems, and the behavior is difficult to predict because of its structure or function, or both. So let's go a little bit into the specifics. I made this very general because I thought there are more people from Lab coming. So I didn't want to start right with complicated things. So in general terms, when you ask the question, where do we encounter complex systems, the short answer is everywhere. Okay, everywhere. Why? Because complex systems combines elements from physics, biology, and social sciences. Let's go through it step by step. Let's start with physics. Okay. Generally, physics is experimental, as you know. It's quantitative, and it's it makes predictions on matter and its interactions. You know that there are the four fundamental forces, which are very different in nature. They happen at different length scales. If you look at gravity and electromagnetism in macroscopic matter, then it exists on all length scales. Molecules, we have usually electromagnetism, also all length scales, but when we go into smaller and smaller structures, atoms, we have electromagnetism and the weak force, right? On the order of 10 to the power minus 18. And then leptons and quarks, we have electromagnetism and weak and strong force. Okay, so these are the four basic fundamental forces that we have in physics. But in complex systems, we have different interactions, different types of forces, and they can coexist. Okay, they happen at the same time. It's not that we can do such a table and we have a clear structure of at which level these forces are present and in which materials. In complex systems, you can have all of them simultaneously at different a different length scale. So when we go very simply to the first, you see, we have here physics. We say it's predictive, right? It's a predictive science of matter and its interactions. So why it's predictive? Because we have Newtonian mechanics, right? Newtonian mechanics. If we take a free fall, for example, we can write a differential equation. We can solve the differential equation very easy. Everybody is doing this in school already. And then we compare the solution with the experiment. And if it matches, then we found a good predictive measure, right? Our theory works. So, and what we can also do in this system, we can fix the initial conditions or the boundary conditions, and we control the system, so to say, right? So only the boundary conditions, especially in Newtonian mechanics, only the boundary conditions influence the motion of the system, and completely determines what happens to the system. Then we go to more complicated systems, right, of many particles and interactions. We theoretically can do it similar, right? We can say we write here a vector x of t that represents the state of the system because it includes all the positions and all the momenta of the system's elements. And then you can write the differential equation. Second derivative of this vector is equal to some high dimensional function, right? It's usually a network. Okay, it's a network that takes into account all the interactions between the particles and all the positions. So, so in order now to be predictive, okay, for such a system, we have to solve 10 to the power 23 Avogadro number amount of differential equations, right? Which is not that easy. I think nobody could do it yet, but you will later see we don't really need it. So in principle, theoretically, this is possible, right? If you, Shai, you mentioned it, if we have all the computer power, infinite computer power, we would be able to do this, right? And this is also something that already in 1814 Laplace thought about, and he had his demon. Of course, he didn't know computers yet, but he had a demon. You know, the Laplace demon, who knows everything. He basically knows how a system will evolve over time. This was a very big thing when Newton and Leibniz developed differential equations. You know, then this really gave a push into the direction. Oh, now we can predict everything. There's no God anymore because we can predict everything. And Laplace made this Gedankenexperiment with his demon. The demon knows all the momenta and positions of the particle, and with this he can predict what is going to happen. It was a big thing in science history. Yeah. So then. Okay, so that's the theory, right? But in real life, we already have problems with three bodies. As you know, astrophysicists, Sun, Earth, Moon problem, right? It's already challenging enough. And Poincaré even showed, I think, in 1887 that there's no general analytic solution. What you do usually is simulations, right? Three-body problem. However, Boltzmann in 1868 or Gibbs in 1902, they said we don't really need to solve all these Avogadro number equations. Why? Because we don't need it. Okay, we don't need it because we have statistical mechanics. We developed the tool of statistical mechanics, and here, with this, we don't really have to worry about the microscopic picture because it comes out, the macroscopic variable comes out just by probabilities. Okay, so if you look at here the velocity of molecules in an ideal gas, it follows this probability distribution, which is called, you know, this probability distribution of particles, non-interacting particles, Maxwell-Boltzmann, right? Maxwell-Boltzmann distribution looks like this. So, of course, it's temperature dependent, as you see. For small velocities, the quadratic term is dominant. For large velocities, the exponential tail. And if you have larger and larger temperature, it kinds of flows gets broader, right? So we don't need to solve the differential equations in order to get this distribution. So it's possible. It's a little bit annoying all the time to have fields covered. So it's possible to derive now to predict how the system behaves and perfectly describe their macroscopic behavior without knowing really or solving the differential equations. The system is predictable at the macroscopic level, and that's nice, right? But I mean, this works only when there are no interactions, right? It's an ideal gas. That's what we said here, ideal gas. And the second thing is the number of particles has to be large enough. Okay? So now we said Newtonian mechanics, few number of particles, Boltzmann, statistical mechanics, 10 to the power 23 number of particles. So you see where I'm driving to. I want to look what is between them, right? Between the two. So we will get to this in a moment. Let's just elaborate a little bit more about the predictability and statistical mechanics. So statistical mechanics, as you know, is a framework to make predictions on macroscopic level for systems composed of many particles. It's probabilistic, and the idea is that we link the microscopic world of components with macroscopic properties. Okay, we explain temperature and pressure by this framework. So many microstates can lead to one and the same macrostate, and the overall task is to compute the probability of these many microstates that lead to a single macrostate. So you have here a couple of examples. So these are macrostates, right? So which macrostate is preferred by the gas and why? Very stupid question, everybody knows it, but let's discuss it a little bit, okay? So these are the macrostates, which one is the, I mean 4, right? But why?
Equilibrium.
Yeah, it's, I mean, to ask the question preferred is not really right? It's not preferred. It is not preferred, but
Most probable.
the most probable, okay? It's the most probable. And this is what you see here. Just you can go and start with 4 particles. Okay, so these are 4 particles here and 2 boxes. And Boltzmann famously said the equilibrium macrostate, so this was state number 4, right? The equal distribution between of the particles is vastly larger than any, so the equilibrium mass is vastly larger than any other macrostate. It contains the vast majority of possible microstates. So we have here 2 boxes with 4 non-identical particles, right? And you can just now draw the combinations, so to say. And you see that this macrostate and this macrostate is very unlikely, right, that this is going to happen, but the macrostate of 2 particles in each of the boxes is the one that is the most likely. It happens for 6 microstates, okay? Whereas here the 1 and 3 only happens for 4, and so on. So this is for 4 particles. So now take 52 particles, and you will see the equipartition is has almost 500 trillion macrostates, right? And this is compared to 1 microstate of 0 and 52. So this is it is not impossible, but almost, okay? So it's just so much more possible that so much more likely that the particles are equally distributed among the 2 boxes, that this is the macrostate, equilibrium macrostate. You can calculate it. You have learned this in statistical mechanics. I don't need to explain you this. And just for you to again internalize it, that it's a purely statistical argument. Okay, now we are coming to this point that I talked before, that we have on the one side we have the Newton-Laplace framework, purely deterministic, predictable, but only when we have very few particles. Then it works very well. Okay, free fall. On the other hand, we have Boltzmann-Gibbs. It's not deterministic. Okay, we cannot solve the 10 to the power 23 differential equations, but it's probabilistic and therefore predictable. Okay, and this only works when we have extremely many non-interacting particles. Okay, 10 to the power 23. So in human society, we only have 10 to the power 9. Okay, we are far away from Avogadro number. So we are somewhere here in between. And this is true for most real-world systems. Okay, real-world systems have strong interaction between their particles or between their constituents, and there are multiple types of interactions that can change over time. So this is where we are with complex systems. We fall in between. Okay. Still didn't answer the question, can we predict anything, right? So, again, here we have the physics that we learn here, usually classical physics, deterministic, statistical mechanics, probabilistic, and quantum mechanics, also probabilistic, right? We have usually fixed initial boundary conditions, fixed interactions in all the three of them. The system's behavior can, in principle, be predicted through analytic approach. This is what we learn in our studies, right, in physics. Complex systems is also probabilistic, okay, but we have an internal structure that changes over time. No fixed boundaries, okay? It's basically the opposite of everything that you see here. We have in complex systems. We have interactions that are not constant but change over time, and the system's behavior can perhaps be predicted. We need to talk about this, but not analytically, but algorithmically. Algorithmically means by simulations, okay? And this is the reason why complex systems only developed in the last 40, 50 years. Before we didn't have computers to do anything, to do any simulations.
Can you give an example for a system without fixed boundary conditions?
A system without fixed boundary conditions is the weather in Israel.
The weather in Israel is not something.
It's not
statistic.
It's complex.
It's complex.
Yeah, you don't have any. You don't have any boundary conditions. Okay. I mean, we have a border, but the weather doesn't give a shit about it. You know? So it's this is one example. There are many examples that just don't come to my mind now. So, right, it's not you don't have just some box with particles that.
But the weather generally is something complex, or is it statistical?
Yeah, no, it's something complex.
Throughout the world, I mean, it's a
throughout the world, yeah.
It's
so the global, I mean, climate is also complex, but you could now argue, yes, but we have here a boundary condition that is our atmosphere.
Exactly.
So I cannot argue.
And this way, just localized, just.
Yes.
Zoom into some
yes.
Maybe.
That's why I said weather in Israel. When I say global weather, there's no global weather. It's different everywhere. Even when we have winter in the north, we have summer in the south. But for climate, you may argue that there's a boundary, which is the world. But I can say, okay, maybe this is a weak argument, but the other two hold. We have interactions that are time dependent, change all the time, right? And we cannot do much with in the statistical sense, and so that's I mean with an analytic approach. Okay, so all of them are going analytic, and with the weather we cannot do anything. Okay, so this is some intermediate summary. So we learned complex systems are composed of many systems that can be described by states such as velocity, position, age, spin, color, wealth, mass, you name it, all kinds of properties. The elements can be anything that interacts and can be described by states. It's called generalized matter. Okay, so for Facebook, we are generalized matter, so to say. Okay, they look at us as a network, and each of us is a node, and our interactions by looking at posts in Facebook and befriending and unfriending someone, so we are behaving for them like generalized matter. Okay, it's not like atoms; it's generalized matter. It's some strange matter, and so the interactions are not limited to the four fundamental forces that we discuss in physics usually, but we have generalized interactions that can be through exchange of messages in Facebook, objects, information in the north by bullets, unfortunately, and so on, right? So all kinds of interactions that you can think about. And these interactions can be described by networks. It's very much dependent on the system is very much dependent on the initial conditions, right? So this is what Nitzan talked about. And we have of driven systems. Some of the complex systems obey conservation laws, some do not. And we have a huge variety of macrostates, not like in a thermodynamic system where we have one most probable macrostate. Here we have all kinds of typical macrostates, and there's no meaning about talking about a typical equilibrium state, okay, in most cases. So if you want to summarize it, as we did before for physics is predictable, only the four forces and so and analytic. Here for complex systems we can say it's quantitative, predictive, and experimentally testable science, okay, of generalized matter interacting to generalized forces or interactions. Good. So much about theory. Now let's, I think this was kind of the physics point of view. Let's go now to, I told you in the beginning that complex systems has elements from physics, life science, and social science. Okay?
Biology.
Yeah, biology, life science. And so this is, so what is the aspect of biology in complex systems? And there are three main points. One is adaptation and robustness, one is self-organization, and one is evolution. Okay? Let's start with evolution. Everybody knows what is evolution. Natural phenomena increases or destroys diversity. Okay, if you want to put it in one sentence. And this can be creative or a destructive process. Evolution is not physics, as we know, because why? Because we don't have boundary conditions. Okay, we cannot look at the system in isolation. If we take some system out of its surroundings, so to say, then we destroy it. Right? It cannot. We alter it and we destroy it. And the phase space of this biological system is not well defined. It changes over time. New elements may emerge because of mutation, right? Or others just disappear. And they emerge on local or global scale. So this is evolution, very briefly. Adaptation. What is adaptation? It is in the sense that many complex systems, especially living systems, they are robust and can adapt, okay, to at the same time. And this is very famously was coined in the 80s and 90s as they are on the edge of chaos, okay. And what it means we will see in a minute. So in the language of chaos theory, you would say that every dynamic system has a maximum Lyapunov exponent, okay, that quantifies how fast two trajectories diverge over time. This is related, Nils, on what you said before. It depends on the initial conditions, okay, how you can predict, how you can say something about the system. So if we write this down very briefly here, so you can imagine you have the distance between two trajectories. You have a system can develop this way and the system can develop this way depending on the initial conditions, right? And if it is a, so these are the trajectory after time t, and at time 0 they met together, and how this develops, okay, are they developing in parallel or do they diverge, is described by this prefactor e to the power lambda t, and lambda is this Lyapunov exponent, right? And now you can have three cases. You can say, what are the three cases? You can have lambda positive, okay, then you have a chaotic system. You can have lambda equal to 0, and you can have lambda smaller than 0. And it's chaotic, okay, you see when lambda is positive, then this explodes, right? If it's 0, it stays basically the same, and if it is smaller than 0, it converges, okay? An example would be, which is not 100%, okay, so don't nail me down on this, but if you think about trajectories, the following trajectories, you want to go with your car from Barilan to Afula, okay? So, and you do this many times, okay? So the chaotic example would be if you go in your car and every time you see a white car, you turn left, okay? I mean, Israel is not so good because you may end up somewhere in Ramallah, but let's just imagine, theoretically. So maybe one day you will arrive in Afula, but the trajectory is very, I mean, it's every time you start your experiment, you will end up somewhere else, okay? So this is maybe an example of chaotic. Also here it's not the initial condition, but it's the condition of
change the improvement.
Yes, but it's that's why I said don't nail me down on
But Nissan can do the experiment today.
I'm actually doing it today.
You're going to Afula?
I'm going to Carmiel.
Okay, wow.
To the north.
So turn left.
Yeah,
Don't do it. Don't do it. So
Every time I see a rocket, I will turn left.
okay.
We come back to the west.
So
To report.
yes, if she will follow according to this rule, she will not be here next week to report about. Maybe at the end of the semester she will come. Yes, so but you get the point, right? This is chaotic. Maybe the edge of chaos, I would say, is using vase. Okay, so you're kind of you don't go all the time the same way. Vase is directing you at I mean vase when you put the option of shortest time. Shortest way is this. Okay, if you always go the same way, you are on a fixed trajectory and nothing changes. Okay, this would be the example of lambda negative, and vase would be on the edge of chaos. Yeah, so I don't know if it's such a good example, but I didn't have something better. I mean, I read something about Genghis Khan. So basically, you know Genghis Khan, right? So you had, I mean, why Genghis Khan became he conquered half of the world, basically, right? And why? Because his father was poisoned, and then he basically revenged the death of his father, and he conquered and conquered and conquered, and by conquering half of the world, he basically pushed the Turks to the west, and they became the Ottomans, and he pushed other groups up to the north, and they became the Russians and the Chinese. So this had a lot of influence, you know, just one little event. If this wouldn't have happened today, and also I think genetically there is a third of us has genes from Genghis Khan. Can you imagine? So I mean, and I don't think this was all the time mutual agreement, you know. So it's very complicated. Yes. So okay. So this is about adaptation, edge of chaos, and the last point I want to make in life science is self-organization. Okay. What is so you may ask how does a system know where the edge of chaos is? The answer is it's self-organized into it organizes itself into the edge of chaos. Okay?
What is the edge of chaos? You keep mentioning that, but I don't know this term. What does
that mean? So the edge of chaos means that your point of exponent is equal to 0. It means that you run your experiment many times, and you look at the trajectory, and the trajectories look very similar. Okay, it's like it's not an attractor. An attractor would be you have all the time the same, right? But it is something that is very similar, so to say. It's and from there it can become quickly chaotic, or it can converge, right? Mm-hmm. So that's the edge of chaos. You're in between, basically. And maybe here on this example we can also again discuss what is the edge of chaos. If you think about a sand pile, you're going to the beach and you build a sand pile. Okay?
Wait a second, Ronnie, please.
Yes.
So when the kind of exponent is equals, let's say 0, so the delta of two trajectories are basically the same. So any small perturbation can take it either to the end of phase or to state.
Exactly. Okay. So it's you're walking on the cliff, right? You can either be pushed in this direction or you can be pushed in this direction.
So it's like on a maximal when you stand right on the edge of the mountain. So it's
you have all
good resting point, but all the possibilities.
You have all the possibilities. Yeah, right. Here. Yes. So self-organization. When you go to the beach and you build a sand pile. Okay. How do you do this? You walk cranes, right? And the pile is building up to a certain level, and then it collapses, right? And then it builds up again and it collapses. So it all the time pushes itself into criticality. And when it's at criticality, it collapses, right? So, so this is an example of a self-organized critical behavior. And this system puts itself always on the edge of chaos, okay, so to say. And when you look at these models more carefully, you see that these avalanches that you get from the avalanches that happen from time to time, they can have any size.
What's avalanche?
An avalanche, how do you say it in
Mapolet.
Marcollet?
Like landslide.
Yeah, landslide. But also snow is also
Avalanche is for snow.
Okay, yes. So you can have, it can have any size. It can be a small one, it can be a massive one, right? Earthquakes are also self-organized critical, earthquake physics is self-organized criticality mostly. You can have earthquakes of all sizes, okay? A few large ones and a lot small ones, right? So if you do statistics, you get power law. Also here, the avalanches of this sand pile, from the sand pile, they are power law distributed, and the times between the avalanches, they are exponentially distributed. So they are random, basically. Okay? When it's exponentially distributed, it's random. And this is an example of a self-organized critical behavior or model. This was suggested actually by Bach, Tang, and Wiesenfeld theoretically, and they came up also with this picture here of sand on the beach. And then Jens Fedder, you remember the guy who wrote this book on fractal, is a very famous Norwegian physicist. He said, I'm going to check this. And he did experiments in the lab. And he said, no, the sand pile is not really self-organized criticality. You don't get this nice power law as suggested by Per Bach, but you only get this in rice, when you take rice, but not any rice, only basmati rice, okay? You need to have, he really checked all this. It was a nature paper in the end. They appreciated all the work he was doing. You need to have this elongated football-like shape in order to get self-organized criticality, because you need the right amount of energy dissipation that you only get when it's elongated. When they are more like spherical, like normal rice, then you don't get this. You don't have this normal distributed avalanche. Yeah, so here just shortly, so how it works, you build up the critical slope, right, and then collapses, and you will have something that's below critical, and yeah, so this is basically how it works. What I was interested in my research actually is that when you go to sleep, when you go to sleep, yeah, now is the right time to go to sleep. But if you study sleep, then you also find that awakenings during the night, I already talked about this a couple of times in introductory physics classes. I don't know if you were present or you remember, but if you, so during the night you have 10, 15, 20 times you wake up, right? Not long enough that you will remember this in the morning, but if I would look at your EEG, at your brainwaves, it looks like you're awake, okay? It's not that you really are awake. I mean, sometimes you're awake and you go to the fridge and drink something, but most of the times it is just inside your brainwaves, imprinted in your brainwaves. So if I do a statistics of your awakenings, they follow a power law, and so they are like avalanches. Okay, one can also model this, that what's going on in your brain. You have sleep and wake promoting neurons, and then usually during sleep the wake promoting neurons, they are suppressed that you can sleep, but sometimes they shoot through, you know, and then you have like an avalanche in your brain that transfers until the cortex, and you see this in the EEG. And the times between these awakenings, they are exponentially distributed. Okay, so this is like here, you wait for an avalanche. Okay, and this is the sleep. So your sleep is exponentially distributed, your wake is polar distributed. I wanted to do some more research on this, but ISF, they didn't give me a grant. They said it's too crazy, so maybe one of you is more lucky with this.
When you're talking about power law distribution, you're talking about the number of places, parts inside the brain that are awake at the same time?
No,
We're talking about the
duration.
duration.
Yes,
of
you have
waking
many times your awakenings are very short, like 1 second, 2 seconds, but then you also have pretty long ones of
time. Okay, so that's
10, 20, up to 5 minutes. Okay, if it gets longer than 5 minutes, you will remember in the morning, you know. But it's pretty, pretty much power distributed. Good. Last point. So this was life science. Now social science. Very quickly. Social science. You know all the social networks we have, social media. So in social science, they study social interactions and implications for society. So examples are game theory. We don't go into this. And we have multi-layer interaction networks or networks of networks. So Shlomo Havlin is one of the pioneers actually the pioneer on networks of networks. Basically, we will talk about this when we have our lecture on networks, but basically what you have is one network depends on the other, right? If you think about the traffic network, it depends on communication network. Right, this is Waze. What is Waze doing? Waze is communicating between the different cars and knows where we have a traffic jam and where you have faster, where the flow is better. Right. So this is one example. In economy, you have the energy network depends on the water network, communication, transport network, and so on. You know, so you have a very network of networks, multiplex networks. So now coming back to the original question, can we predict the future? Now you should have a more, how to say, you can discuss it in more detail, I hope. So what would you say now? Can we predict the future? Anything?
What do you plan of exponents?
Hmm?
What do you plan for the trajectory
Yeah,
one plans?
yes, so this one aspect. But basically, I mean, you got it right when you said it depends. Okay, it depends which future of what, right? The future of stone falling to the ground. It's very simple. It's Newtonian physics. I can predict it.
It does not follow a complex.
Yeah, I mean, yeah, it's the future. The future of what? Is the question. What system? Yeah. Is it a Newtonian system? I can predict it. Is it a statistical system like gas in some between boxes? I can predict it. Is it a complex system? Is it a complex system? I can also predict it sometimes. Okay, we haven't learned yet under which circumstances we can predict it, but it's sometimes possible. So the answer to this question is it depends. Okay, basically. And I wanted you to, and this is something that when they discussed this question 200 years ago, they didn't have all this background. Okay, so if you would sit nowadays with Laplace, you could teach Laplace basically and Newton about predicting the future. Okay, for them it was all differential equations. They didn't think about in terms of complex systems. Yes. Okay. So that's the first. Let's do a break maybe, no? Let's do a 10 minutes break and then continue. We have time until...
After you.
If you... Or you don't need a break.
How much time do we have?
It will be until 2, maybe another half an hour. 40 minutes.
What do you think? We can continue.
If you want, then we can continue, yeah. Good. So this is the basically the introduction. So let's summarize it briefly. We have
just to mention,
yes.
Also the frequency of stellar flares follows the power law.
Exactly, yeah. It's also self-organized criticality system. Solar flares, I forgot to mention this. Yes, thanks. Yeah, so summary here. Systems with many similar parts. Atoms, molecules, cells, people, animals, computers, blah, 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 and so on. The behavior of the system is not just the sum of its parts, as we said, and something interesting must happen. Okay, we said it's called emergent behavior. So, and this emergent behavior only happens when I have interactions between the particles. I do not have emergent behavior in ideal gas. It cannot be, because it's very boring. Okay, there's no emergent behavior. Another example is where you have many elements and no emergent behavior is you have a bucket with marbles. You put the marbles on the floor, nothing really happens, right? It's very boring. So, more is different was what Phil Anderson said about complex systems. He is one of the big, you probably know him, right? Phil Anderson, famous physicist, is high temperature superconductivity. He had many contributions to complex systems, to anonymous diffusion, many contributions. He worked in Bell Labs. More formally, you can say complex systems are co-evolving multi-layer interaction networks, but this may be a little bit too abstract. Okay, so let's talk a little bit more about this emergent behaviors. When we have an ecosystem, emergent behavior, we said is evolution, right? Market, when we look at the market economy, the emergent behavior is price setting. Okay, how people, how certain prices are determined. In Israel, I don't think it's an emergent behavior. In Israel, it's Tnuva meeting Strauss and ask them how much do you think we should charge these suckers for the cottage? Yes, but in general, for a big economy, it's an emergent behavior. Road traffic, it's the emergent behavior of traffic jams. Okay, and human organism, one of the emergent behaviors is sleep. Okay, that happens. So. And now let's get a little bit more into specifics. Understanding complex systems, we can do some analysis. We have to develop the right algorithms and modeling. Okay, let's start with the models. We can have two extremes, right? You can have the physics spherical car model, and this would be simple. And we have the complex model where we really look at the car. So this simple model gives us a good understanding of the mechanics, right? But it's not very accurate. So we can, for example, explain when two cars collide with each other because they are fighting, which car will push the other car away. Because it's just depending on their mass and kinetic energy. Okay, so this would be an easy first semester mechanics question. Not very interesting for anyone else, but for physicists perhaps. On the other spectrum, so this tells us a little bit how the world works, very simplified and very simplified terms, and it's used in basic science. On the other spectrum, I have a complex model, okay, where I do not simplify so much. I look at the cow as the cow is, little understanding, and I usually can give good quantitative accuracy. I can make good predictions, and this is usually used for government bodies, industry, finance world, banks, and so on. and the farmer, you know, who wants to understand why one cow is fighting with the other, and perhaps because the one ate the food of the two cows actually fight. No, cows do not fight. Right?
Maybe over females.
The bulls maybe fight. Yeah. Yeah, but for this you cannot answer with the spherical cow. You need to know if it's male or female, okay? And it starts already to be too complex for physicists, maybe. So another example is it's called. It's also a very simple model. It's called the Nagel-Schreckenberg model for traffic. It's a cellular automaton. If you have heard about it, and it's just a model where a car hops from cell to cell. Okay, so you have many cars that hop at the same time from cell to cell. Not very realistic, because cars do not hop in the same lane, and they also cars usually change speed, right? And cut you, especially here when you. Yeah. You will see this a lot today when you go to the north, cutting and honking and stuff. So very unrealistic, but you can see already. What did we say? We want to see an emergent phenomenon, right? We have some simple model. If it's complex, we want to see an emergent phenomenon. Let's see if we can see anything. And here there is some simulation. It's a nice package. It's called NetLogo, where you can have all kinds of statistical physics simulations. And we go to traffic.
We don't say that. We only show the.
Okay, that's a good point. How can I take it out? To go to the end show, right? And now you see it. Yes. Okay. So we go to traffic. Basic, and so we set up the cars that hop from cell to cell. Set up. So here you see these are the cars, and here's our red car, and it has periodic boundary conditions because.
And how are they distributed initially?
Hmm?
How are they distributed initially?
Initially, it's random.
Oh.
Yes, and you see everything is going nicely, right? With the red car, it's going and going, but now you introduce also that they can not only accelerate but also decelerate. And look what happened. What happens? Let's reset up again and. This is our emergent phenomenon. We get traffic jams, right? Just because they are accelerating and decelerating. If they would just accelerate, you would not get a traffic jam. But by accelerating and decelerating, you get a traffic jam. And you see that the traffic jam is actually moving in the opposite direction of your flow, right? So this also explains why sometimes you have a traffic jam and then and you don't know what's the reason for it. Spontaneously happening traffic jam. Why? Because somebody was braking and everybody behind also brakes, and this way you have kilometers behind this guy, you have traffic jam. Right? This also reminds you of something. I mean, this looks like
a wave.
Like a wave or when you think about semiconductors, right? You have the current flow in one direction and the holes are flowing in the other direction. So this is also something you can use to model this. Right? Very interesting, simple model, emergent phenomenon, and you can now do some small studies. You know what is the relation between acceleration and deceleration, that you get this traffic jams, how do you best dissolve the traffic jams, and so on. So it's nice little toy model. And so this is on the one spectrum, and the other spectrum is having, I mean, nobody's doing this, right? When they simulate traffic here in Tel Aviv, they don't use Nagelstrecken. They have this kind of complex models, right? Here is an example where they take really many variables into account. Okay. So here this is okay, doesn't matter, it's not giving the right thing, but it's just something that shows you how complex real traffic models are, and what kinds of variables you have to collect in order to get really predictive measures. Good. So so these two things, Nagel-Schreckenberg and the other complex model that I didn't show you now, but you can look at it at home. These were examples of deterministic models. Okay, I can exactly predict what's going to happen just because of all the ingredients and relationships between them. Another kind of model are stochastic models that include random components, and the problem is when we simulate them on the computer, they are not, so the computer cannot really give us strictly random numbers. Okay, a random number generator on your computer is not really random numbers, because the computer is a deterministic machine, right? Strictly random numbers would be radioactive decay. Okay, radioactive decay is when they, in some experiments, they really need random numbers, okay, and the random numbers you get from the computer, they are not good enough. So in this case, they use radioactive decay in order to generate random numbers. Question, you know Brownian motion, right? Brownian motion. Is Brownian motion strictly random or not? What would you say? So random, you have here Brownian motion, you know, right? You have the water molecules and they push here some.
It's deterministic because you have all the parameters.
Right, right. Actually, you could, if you had enough computer power, you could calculate this, right? Could calculate this because it's just collisions between particles. So, so the answer is it's not strictly random. However, we cannot predict its trajectory because we don't have enough computer power. So, it's for most application good enough, okay, random enough to use. And another example is that throwing dice, it's also not strictly random. Why?
It's Poisson. No, it's.
Why it's not strictly random?
It follows the Newton physics.
Yeah, if you would know exactly the angle on which corner the cubia hits the table, you could theoretically calculate what number it's going to show, right? So it's not strictly random, but unpredictable. Okay, so and you can use it to generate random numbers. It's good enough for most applications. So just a couple of examples. How many times you have to roll a die in order to get number 1?
It will vary.
In average 6 times, right? Average 6 times. Average 6 times. This 6 times on average. Easy. How many times you have to roll a die before getting every number at least once? You know this?
6 to the power of 6.
It's too much.
Difficult. But you can do it in 2 minutes with the computer simulations, right? So you can just here, couple of lines of code. You do you run this experiment 10 times. You have your array of numbers 1, 2, 3, 4, 5, 6, and you roll the die, and every time you get a number, you kill it from your list, and you print how many times you have to go through your list. And in first experiment 26 times, then 8, then 16. You know, you print out how many times, and then you do a distribution. Okay, this distribution. So sometimes I need it 50 times until I covered everything, but it's not very likely. Okay, so on average it's around 14.7, 14.8, and you can also calculate this analytically. It's a random process, but I can calculate it just by, it's a binomial process. Okay, it's 6 over k, and you have to sum 6 plus 3 plus 2 and so on, and you get 14.7. Random process, but has an exact mathematical answer. Okay, it's nice. And even nicer is that Ullmann, Neumann, and Metropolis, they could show something very significant in statistical physics. In the 1940s, they could show that you can solve all kinds of physics problems if you find the appropriate random process that has the same result as the mathematical problem. It's called Monte Carlo simulations. You probably have heard about it. It's used a lot in physics when you do simulations. And one very simple example is using Monte Carlo simulations to integrate something. Okay, numerical integration is you can do by Monte Carlo simulation. Imagine you have here this function, which is a quarter of a circle, right? Quarter of a circle. So it's 1 minus x squared square root, right? And you should calculate the area. I mean, we know that the area is 1/4 of pi, right? But you have to do the integration numerically. So how do you do this? In a Monte Carlo simulation, you would choose 1,000 uniformly distributed random numbers. So very important that they are random, right? And then you just throw them without looking. So I'm standing here and I'm just throwing random numbers on the screen, right? So there's a probability that they fall inside the circle, then they are green, and outside the circle. Okay, then I cover them in pink. And then I just calculate how many are inside divided by how many I was throwing on this. Okay, and this gives me an estimation of this area. I multiply this area by 4 and I get an estimate for pi. Okay, this is a nice example for Monte Carlo simulation, and you can you can program this yourself. It's a couple of lines of code. Here you choose the random numbers, x, y. It's a tuple, right? It's x, y coordinate, and then you have you ask if these numbers fall within the circle, a quarter of a circle, then I count my hits. Otherwise, I do not, and then I calculate 4 times the number of inside the circle divided by the total number of the total overall number. And then you see when you do this for 10. So here, here I wrote it for 10 realizations, but here when you do it for 100, okay, for 100, if you take only 10 random numbers, you get already pretty close, 3.17. But if you take 1 million, you get it until the 4th digit, number pi. So this is the power of Monte Carlo simulations. And actually, this throwing random numbers and calculating, integrating something numerically, this very much is similar to a game they had already in the 18th, 19th century, when they didn't have YouTube and all kinds of media to not to get bored in the evening. So what they played is something that's called Buffon's needle, and you put on the floor some stripe pattern, and then you are throwing needles, right? And the objective was to hit the line, okay? And who hit the line, who got most of the hits, was the winner. Or you could say between the lines, that doesn't touch, you know. And one guy, his name was Lazzarani, he estimated just by throwing 3,400 needles, he estimated pi to the 1, 2, 3, 4, 5, 6, 7th digit. But it's, I mean, he said this, but people nowadays agree that this, I mean, he was not lucky, he was cheating. And they explain by Wikipedia, you can read about it. It's a very interesting story. Yeah, but so this Monte Carlo simulation was already around in the 18th and 19th century, but people didn't call it like this. And yeah, so and the last example I want to show you, also Monte Carlo simulation, is a diffusion limited aggregation. So you can imagine the following: you have a reservoir, and inside the reservoir you have particles swimming around, okay? And when they meet each other at the beginning, they form a nucleus, okay? And then any particle that hits the nucleus is going to stick to it, okay? And then you grow such nice shapes there, okay? Why it's not just becoming a solid? Somebody can explain it? Why it's not just becoming a sphere that is
maybe because we have particle stacks between the different.
Yeah, it's much more likely that you hit your structure at the outside than to diffuse until the middle, right? And this way you get these nice shapes, and you can grow these corals. You know, you can grow corals by the computer, and here's a nice, beautiful YouTube video you can look at. It's very relaxing. You cannot sleep in the evening. It has a nice sound, and you see nice structures. So it's good to relax, but not now, because you will fall completely asleep. So these are examples of corals that are produced by the computer, and they look. I mean, you cannot distinguish this from real corals. What does this teach us?
They want to have more body surface to have more contact with the stuff?
No, simpler. It just teaches us that
One can model the growth.
the way nature is growing these Corals is by diffusion limited aggregation. It's exactly the process that describes nature. So this is what I told you before. You want to explain a physical phenomenon, right? So here we said this about von Neumann before here. So we want to solve a physics problem, okay, that is how coral is growing, okay, and we find a random process. This is sticking together these particles, diffusion limited aggregation, that has the same result as the real process, okay. So this is the power of complex systems and of these algorithms to explain nature. Good. So that's it for today. Any questions?
Was it mere luck, or that these two looks the same, or can we actually explain why TLA acts as the same as car growth?
Yes, we can explain it because the corals also actually the corals do the opposite. So in the diffusion limited aggregation, you have the already existent structure is catching the particles. I mean, they are all the time in the surrounding, and only when they attach to the structure they become visible. So for the coral, it's the opposite. That basically what is not strictly attached to the structure is going to be washed away. You know. So this way you need to. I mean, I don't have a deep understanding of the growth of corals, but they basically they grow by losing the particles on the edges, so to say. But
I can read it by myself.
I need to look at it more carefully. I don't know exactly. But you get the same result. That's fascinating. And you get these different kinds of shapes simply by changing the way the particles are moving in the medium. If it's more viscous or less viscous, if you have more interactions between the particles, if you have stronger interactions, you get more compact shapes. If you have less interactions, you get more this kind of shapes. So you can this way you can study also the different regions in the world that show different coral reefs. You get some understanding about the environment there. You know. Yeah. So that's I find interesting. Good. So next week we.
By the way,
yes.
I think next week we don't have a lesson. I think there is a break because the university starts. I think they have
Is it not on Wednesday? Wednesday or Thursday? I thought it was on Wednesday.
I can check it out in a second.
The 6th, I thought it was.
Wednesday, yeah, you're right.
So the 7th is okay, good. Yeah. Okay. So thank you. See you next week.
Thank you.
And of course, I didn't say it, but if you think you do something in your research that is related to complex systems and you want to share some kind of algorithm or method, like Imri, you're doing something interesting.
Imri will share.
Then you can tell me, we have the time for it, and I think it's interesting for everybody to see.
So now we need to summarize it in our logbooks back at the lab and start writing in the...
you don't have so much yet. So
no, not yet.
Today was more blah blah. So it was more general introduction to give you a taste of complex systems. I hope it was not too boring, but you don't have. I mean, you can maybe write one paragraph about complex system is something with not too many particles, but not too few, and interactions are important, and emergent phenomena, emergent behavior. So maybe you can write half a page or something.
Thank you.
Good. Thanks.
Thanks, Ronnie.
בוא נעשה קצת עצמי.
No, that's.
לא עושה תמצית.